All right, so continuing our introduction to differential equations from last time, this time we want to look at some more applications of it, but using a lot of the same skills we saw from before. So first, I got some quick examples in which we want to come up with a general differential equation and then separate the variables. So for the first one, we have the growth rate of a bacteria in a petri dish is proportional to the number of bacteria. So we can say, therefore, the derivative of bacteria with respect to time, if it's proportional to the number of bacteria, that means it's the same as just k times the number of bacteria. K being some value, we can't say what it is because we're not given enough information. So there's the differential equation with that proportion k, that constant k. And if we knew more information, we could figure it out. That's it, to separate the variables, divide both sides by divide both sides by b, and we get 1 over b times db. On the other side, we get whatever that constant is times dt, and we can integrate that fairly quickly. All right, this time we have the increase of the radius of an inflating balloon is inversely proportional to the square of the current radius. So that means dr dt it's k divided by the radius, because it's inversely proportional, but it's the square of the radius. So it looks like this. That's inversely proportional to the square of the radius. And so if I want to separate the variables, I would then get just r squared times dr on one side and k times dt on the other. All right, the rate at which water flows out of a bucket is proportional to the square root of the volume V remaining. So that means the derivative of V with respect to time is equal to some constant K times the square root of the volume. Now that said though, because the water is flowing out of the bucket, we know this derivative will be negative. And so quite often we put a negative right here in front of the K, basically just to ensure that we know this derivative is negative. If you don't have that there, we should just know that our K value, whatever that constant will be a negative number. So I'll stick with this. So now to separate the variables, I'm going to divide both sides by root v, which is the same as v to the negative 1/2 times dv on one side, and just negative k times dt on the other. All right, lastly, the rate of increase of the number of people with the disease N in a population of size P is proportional to the number of people with the disease and proportional to the number of people without the disease. Okay, what does that mean? Well, first, the rate of increase of the number of people with the disease, N, so that means we're looking at dN dt, is proportional to the population, the number of people with the disease, so it's proportional to K times N, and proportional to the number of people without the disease. So this is also being multiplied by another value, which is who doesn't have the disease, which in this case is going to be the whole population minus N. And so that there is our equation. And now to separate the variables, notice everything here, N is the variable, but P is a constant, or P is, we're not differentiating with respect to P, it's the population given. So I want to divide both sides by N times P minus N. And so if we separate these variables, we get 1 over N times P minus N on one side times dN, and on the other side, we get just that proportional K, that proportional constant K times dt. All right, now quite often we're already given equations, but sometimes we're not, and so let's look at some slightly more involved examples. So here we have the mass of a radioactive substance. It decays at a rate proportional to its current mass. Initially, the mass of the substance is 25 grams, and the rate of decay is 5 grams per second. So let's find that constant K in the differential equation, dm dt equals negative Km. So notice we got the negative there, so our K will be a positive number. It's decaying, so I know that negative K altogether must be negative. The negative's already there, so I want to know what K is. All right, so first let's get that set up. 1, and essentially just write down what we have. dm, the change in mass over time, is minus Km. So that's it. We're told that at the start, this mass is 25 grams, and the decay is 5 grams per second, which means it's losing 5 grams a second, which means I know dm dt is negative 5 when m is 25. Now I can solve for k quite quickly. Essentially divide both sides by negative 25, and we get k equals 1/5, which means my equation, even though I'm done the question was asking what is k, there's k. However, that means my equation here for the differential equation, we can say dm dt equals minus 1/5 m. That proportional constant is negative 1/5, just the negative was already given to us. Okay, so for part 2, I'll do that down here. I'm going to need a bit of space, though. I now want to find the differential. I want to use that differential equation to find an expression for the mass of the substance after t seconds. So I want mass as a function of t. I have the change in mass as a function of mass. I want to find mass as a function of t. So I want to find the solution to this differential equation. And so first I need to separate the variables. And so looking at this, to separate the variables, I want to divide both sides by m, and then multiply both sides by dt. And we should pretty quickly get to something like this, where I have 1 over m dm equals negative 1/5 dt. That's taking the equation there, again, dividing both sides by m and multiplying both sides by dt. I want to integrate this right away, so let's integrate this. And so on the left-hand side, that is our natural logarithm. I could say the absolute value of m, but m is a mass, so mass has to be positive, so I don't need to think about that. I could say plus some constant, but there's going to be a constant on the other side as well, so I'll just leave that for now. On the other side, negative 1/5 dt, the antiderivative of that is negative 1/5 t plus some constant. I'll call it c1. All right, to solve this equation, I now want to solve for m, so I'm going to raise everything as a power to a base of e, which means the natural logarithm cancels out. So I have m equals e to the negative, I'll write it as t over 5 plus c1. Well, we've seen this in previous lessons. Adding this constant in the exponent is the same as multiplying all of this by just e to whatever that constant is. But now let's think more about this constant. This here, we quite often, we saw this before. This is just, that constant is a rather arbitrary number right now. So e to the power of that constant, I'm just going to call this whole thing c and write it first. So I'm going to have m equals some constant. Now it's just c times e to the negative t over 5. But this c here means something, and I can tell what it means, and if I give myself a bit more space, so let's sneak up here. This c here must represent the initial mass. How do I know that? If I look at this, if I make t equal to 0, then I know that this becomes e to the negative 0 over 5, which is e to the 0, and e to the 0 is 1, which means when time is 0, all of this is 1, which means when time is 0, the mass is whatever c is times 1, which means when at time 0, the mass must be the same as c. So I know that c is the initial mass. And we see that quite a lot here. And so I'm going to make a little note that I now know that c must equal m naught, which we are told in the question is 25 grams, which means I actually know my equation now. So my equation is m equals 25 times e to the negative t over 5. And that is the answer for part 2. That is an expression for mass as a function of time. Now I want to use this to find the half-life. So half-life is how long it takes for it to go from any mass down to half as much. We can see it starts at 25, so one thing I could do is use this equation to figure out how long does it take to go from 25 down to half of 25. So let's make for part 3. Let's solve for 12.5 equals 25. That's a messy 5. 12.5 equals 25 to the power of e over e to the power of negative t over 5. At this point, we could solve this graphically. We could solve it algebraically. I think it's pretty quick to solve it algebraically, especially if you want an exact value, which we can get pretty nicely here. So I'll divide both sides by 25. We get 1/2. Give myself a bit more space. These questions don't quite fit so nicely on these pages anymore. A little more involved in earlier lessons. So I get 1/2 equals e to the negative t over 5. If I want to solve for t, I'm going to find the natural logarithm of both sides. So I get the natural logarithm of 1/2 equals negative t over 5. So now to solve for t, multiply both sides by 5, divide, or negative 5 actually, or divide by negative 1, however you look at it. Our exact value is t equals -5 times the ln of 1/2, and that's in seconds. Or we could approximate it, and we should get about 3.47 seconds. Keep in mind the question did not ask for an exact value, so you're more than welcome to give an approximation to 3 significant figures. You're also more than welcome to solve this graphically, although in this case, that shouldn't take too long to solve it algebraically. All right, lastly, we have a hamburger is placed on a grill. It starts at 40 degrees Fahrenheit, and the grill is at 400 degrees Fahrenheit. After 10 minutes, the hamburger is 107 degrees. So we want to determine this constant R in this equation here, in which capital T is the temperature of the hamburger, and TS is the temperature of its surroundings, the sort of ambient temperature around it. And so TS is a constant in this. And notice the structure of this is actually quite similar to what we did in this last example up here. So the first thing I want to do is substitute at least 400 for TS, because it says the grill is maintained at 400 degrees Fahrenheit. So for part 1, the first thing I want to do is write that out and say dt d small t. Okay, so big T is temperature, little t is time, equals R, which we're trying to figure out, of 400 degrees minus the temperature of the hamburger. So that one's changing. All right, how do we figure this out? Well, let's separate the variables and integrate this and to determine the general solution to this differential equation. So in this case, I want to separate my variables, so I'm going to divide both sides by 400 minus t. And so on this side, I have 1 over 400 minus t times d big T. On the other side, I just have R times d little t. And I want to integrate each of this. So on the left-hand side, 1 over 400 minus t is going to be related to the natural logarithm. We got to be careful, though. There's a negative right here. So we could do integration by substitution, or we could do a little bit of analysis. I can kind of, it's fairly quick to do a little bit of guess and check. You may guess that it's going to be the natural logarithm of 400 minus t. But if you check that, that leads us to a derivative of -1 over 400 minus t. So all I got to do is make this negative. And then you can check. Plus some constant, but I'll have a constant on the other side anyways. On the other side, R, remember, is a value we're trying to figure out. It's a constant value, so it's really a constant that we're finding the antiderivative of. So this will just be R times t plus some constant, which I will call C1, because I'm fully prepared that I'll probably have to adjust the form of this. All right, I want to solve for big T, which again is the temperature of the hamburger. I don't like that negative in front of the natural logarithm, so I'm going to multiply everything by -1. So I now just have the natural logarithm of 400 minus t. Over here I have minus RT minus C1. Although I don't need to get too hung up on the fact that constant is being subtracted, the constant itself could be a negative number. As well with a natural logarithm, I don't need to worry about absolute value. Everything inside there is representing a temperature in a barbecue. It's not going to go into the freezing point temperatures, so I'm good with just having those regular brackets. I want to solve for big T. I'm going to raise everything to a exponent with a base of e, and so that leads me to 400 minus t on one side, and on this side I have e to the negative RT times e to the negative C1. That's it. Like we've seen before, this here is a constant that I'm just going to call C, and I'm going to write it as a coefficient in the front. And so I now have 400 minus t equals C times e to the negative RT. Okay, so what is C? It's not quite the starting temperature here, but we can still figure out what it must be, because at time 0, we make this time 0, then all of this becomes 1. And at time 0, that means, what do I have here? T, remember, is the temperature of the hamburger. At time 0, it tells us the hamburger starts at 40 degrees. So I'll make a little note here. At T0 equals 40, which means C, at the start, C must be 360. because at time 0, the left-hand side is 360. That's the difference between the grill temperature and the burger temperature. And at time 0, that must be the same as the right-hand side, because at time 0, my exponential part just becomes 1, which means I know C is 360. So now I know my equation here. My equation, especially if I isolate T, I get T equals, I'm going to write it like 400 minus 360 times e to the negative RT. I still don't know what R is, but I'm getting close. All right, so now let's solve for R. Let's figure out R. Up here. And to figure out R, I now need to go back to my question and realize I've never used the fact that after 10 minutes, the hamburger is 107 degrees. So I can go back to this and change big T to 107, change little t to 10, and I have enough information to solve for R. And so let me substitute that in here. I get 107 equals 400 minus 360 times e to the negative 10R. And now I can solve for R. Depends how exact you want to be. Should be pretty quick to do it algebraically. Subtract 400 from both sides. You get negative 293 equals negative 360 e to the negative 10R. Divide both sides by negative 360. We get, I'll write as a fraction, positive 293 over 360 equals e to the negative 10R. Find the natural logarithm of both sides. Divide both sides by negative 10. We get to an exact value if we want, but we don't need that. So we should get to R being approximately 0.0206. Now, there's more accuracy in my calculator, but we have question 1 done, which is what's the value of R. That's it. Even though they don't directly ask for it, I now want to write down my equation. So my equation now, because don't forget, my equation was almost done back here, and I now know what R is, so I just want to substitute R with that approximate value. So my equation that models the temperature of the hamburger is T equals 400 minus 360 e to the negative approximately 0.0206 times T. Keep in mind there's more value accuracy for that on my calculator. And now for part 2. How long does it take for the burger to cook? It's cooked when it gets to 160 degrees. This should be pretty quick now. The hardest parts are definitely done. It doesn't ask for an exact value, so essentially for part 2, I just want to take this, and we know we want to make this temperature 160, and we want to solve for T. Because this is a little bit more messy than the previous question, I would just solve this graphically. I would just graph 160 on one side, graph 400 minus all the other good stuff on the other. And so I would solve any way you want. You can also solve it algebraically using natural logarithms. It shouldn't take you too long. You just want to think what you're going to be faster with. That's a matter of opinion. You should get T being approximately just shy of 20 minutes, 19.7 minutes to 3 significant figures. So about 20 minutes to cook this burger. That takes a while to cook the burger. Takes a while, probably about how long it took to answer the question. Whew.